Hi, I'm Rainy, and this presentation is about the unified and interpretable emotional representation and expression generation. Expressing emotions plays a huge role in our everyday lives. That's our primary way of communication. Unfortunately, understanding emotions still remains a very challenging task. To determine what emotion a person feels, we judge solely on what we see, facial expressions. That is why we can use emotion models to help us when processing millions of images of people's facial expressions. Let's look at the most commonly used emotion models. The first one is the categorical model. Here, each emotion can be classified into 6 different categories: sadness, anger, surprise, fear, disgust, and happiness. In the compound emotion model, the compound emotions which are made by combining some of the basic emotions are also included. There is also the action units model, where we rely on the activation of the facial muscles. But emotions are continuous. That is why people use the arousal valence model, where each basic emotion can be represented by a vector on the 2D plane, starting at the origin. But by using this method, we can represent only 6 out of the 17 compound plus basic emotions by using 2 consecutive in the 2D plane vectors. Our model, called the C2A2 model, unifies all 4 categorical, compound, arousal valence, and action units models into one. So how do we construct our model? We use the idea from the arousal valence model, but we leave the vector for one of the emotions above the plane, we chose fear, and we lower the vector for another one of the emotions down, we chose sadness. By doing so, we can now use all points in the 3D space to represent different emotions, and we can represent a whole 15 out of the 17 compound plus basic emotions using all of the planes formed by 2 consecutive vectors. We also propose a method to generate continuous expressions from the C2A2 model. To do so, we modified Dreambooth to understand numbers so that we can use the 3D coordinates of the emotions as a prompt in our training and sampling. For the training, we use images from the AffectNet dataset, and as a prompt during the training, we use a text and a number embedding. For number embedding, we use a number encoder. We give it as an input the 3D coordinates of an emotion, and it outputs an embedding of the 3 numbers. Then we merge the embeddings of the text and the numbers and give it as a prompt to our text-to-image model. We compute the emotion reconstruction laws between the generated images and the training images. Then we use random images from the AffectNet dataset for our regularization images. This time we don't use any numbers in our prompt, we just use a text caption. We feed it to our shared image decoder and compute a prior preservation laws between the regularization images and the generated images from our model. For our quantitative analysis, we compute different metrics: the FEG, ERE, and the smoothness score, and as we can clearly see on all of them, the C2A2 model performs the best. We also computed the softmax score for radiuses between 0.02 and 0.3 along the happy axis to show that our model is good at generating subtle emotions. We've conducted a user study in which 8 expert psychologists rated 315 images from each method on the scale from 1 to 5, with 5 being the highest, by how much they agree with the coordinates of the images. The results are summarized in this table. This table shows the average ratings for 7 compound emotions that can be represented by our C2A2 model, but cannot be represented by the arousal valence model, the average of these 7 emotions, and the average among all emotions. As we can see, our model clearly outperforms all of the other models. We also compared the FIG and the user ratings for 6 different methods. Our 3D representation method represents the best combination between low FIG and high user rating score. The 2 methods with low FIG often fail to represent the targeted expression. For our qualitative results, we generated images using 5 different methods and compared them with images generated by the C2A2 model. In the table on the right, we show that our methods can preserve the attributes from the base network. This allows us to perform meaningful number plus text-to-image generation. This table shows 9 compound emotions that can be represented by the C2A2, but cannot be represented by the arousal valence model. When compared with other methods, our 3D-based representation is clearly superior, thanks to its richer representation and the continuous number understanding capabilities. Summary and acknowledgements. The paper introduces C2A2, a new unified model for understanding and representing emotions, addressing the gap in current literature by integrating canonical, compound, action units, and arousal balance modalities. We develop a method to annotate emotions using the unified model and adapt text conditional diffusion models to generate nuanced expressions, demonstrating the model's effectiveness through experiments and offering a refined approach to emotion representation. This research was partially funded by the Ministry of Education and Science of Bulgaria. Support for Insight. Thank you.